Hello everyone. Am I audible?
Yes, ma'am.
Okay. Okay, fine. Venugopal has one doubt. Please go ahead. Unmute yourself and you can ask the doubt.
Ma'am, I'm having a small doubt in when to use omega S. Omega S is equal to for every hour we will take 15 degrees increment. 12 at 12 noon we take 0 and accordingly positive and negative. If it is going below 1 o'clock means negative and below means above means negative positive. But sometimes we are also taking omega is equal to cos inverse tan phi and tan delta. So when to use these two different things, ma'am? Omega yes.
Okay. So, see, one is our angle that you are talking about, and the second thing is our angle corresponding to your sunrise and sunset. Okay. So, if you're just talking about uh, this hour angle, say for 1 o'clock or maybe 11 o'clock, then you are calculating it corresponding to 12 o'clock solar noon. Okay, in that case, you take the 1 hour is equivalent to 15 degree. But if you're talking about omega s, that represent your hour angle corresponding to sunrise and sunset, and that for that you have derived that formula of cos inverse minus tan phi and tan delta, I think. So I hope that is clear.
Hmm? Means omega s stands for only how many hours the sun will shine.
Right.
That is
Omega
the thing.
s basically help us to calculate the total day length. So the day length is 2 by 15 omega s. So it basically tells us about from sunrise to sunset what was the whole, uh, rather than calculating in hour, what is it in term of our angle, and in term of that then we can calculate the day length.
Yes, ma'am. We were calculating that is of day length, like 14 hours, 12 hours, 8 hours, something like that. But sometimes we are using omega s is equal to, without using 2 by 15, we were using omega s is equal to cos inverse tan phi and tan delta.
No, you haven't, so let me show you. Okay, so I think it was in week 3, right? Okay, not in week 3, but okay. But you might have not paid attention to the formulas. Let me show you the lecture, then I can. So I think it was in fifth or sixth. So let me show you. Okay. So omega, the thing that we are, so sometimes 2 by 15 omega is directly used to calculate the day length. But for omega s, your formula is cos inverse minus tan phi and tan delta. That too varies in the northern and south here. Okay. So you can see that omega s is for like our angle corresponding to sunrise and sunset. Its formula is given here. So omega is just for your hour angle that can be calculated for any hour, any time of the day. But omega s specifically tells you about the sunrise and hour angle corresponding to your sunrise and sunset. So based on that, you can calculate your day length. That is 2 by 15 omega s. That is 2 by 15 cos inverse minus tan phi tan delta. Okay. So is that clear?
Ma'am, for suppose for example, directly we are taking no ma'am. At 12 noon we are taking 0.
Uh,
For omega yes, then no need of using this cos inverse minus tan phi tan delta.
no, no. So
That's why.
see, if you are going to calculate it, say omega s, you are going to calculate it for a particular time of the day, right? So you can calculate it for 11 o'clock or say 9 o'clock. You cannot calculate it for from say 6 o'clock to 6 o'clock in the morning to evening. For that, you need to integrate this whole omega s corresponding to the day length, and then you, so that derivation has been simplified, and this hour angle has been got. Okay, are you getting my
Okay,
point?
okay. Ah, yes, ma'am. Yes, ma'am.
So
Yes, ma'am.
I think I have explained it well in one question also. That have I think I have explained in which lecture that I have to see, in which session. So just a minute. So I think it was week 3. Mm. So at last I have taken one question where I have specifically mentioned that when to use omega and when to use omega s. Uh, so we'll go back to the lecture. Let me see the question that. Uh, Okay. See, in this question, it was asked that calculate RB for a surface at a latitude of 15 degree north, at a tilt 30 degree toward the south for the hour 9 to 10 solar time on February 16. Okay. So if you have calculated the RB, the small RB, okay. So you are talking about a particular hour, say 9 to 10, and for that particular 9 to 10 hours, you can calculate omega at one particular time only. The formula that we have, 1 hour corresponding to 15 degree, if you have to apply it, so that's why we go for an average value between 9 to 10 that correspond to 9:30, and for 9:30 you then calculate the hour angle. So it will be 15 degree till 11, and then 15 degree till 10, and then halves, so 9:30, 7.5 degree corresponding to 9:30, so you will add this and your omega will be 37.5, right? But if I'm going to calculate it for the whole day, right, so then here comes this formula omega s, for a horizontal surface, and omega st for your tilted surface, where beta will be included, that tilt angle, and then you get this omega st and put it into the equation. I hope you got the difference between both these things.
Yes, ma'am. Yes, ma'am.
Is it clear?
Thank you, ma'am. Yes, ma'am. Yes, ma'am.
For sure.
Yes, ma'am.
Any doubt?
No, ma'am. No.
Okay. If you still have any doubt, you can go ahead, ask if you have any lingering doubt.
No, ma'am. No.
Okay, okay, that's fine. Okay, so okay, so it's already 8:18, 6:18, so we'll start the session. So welcome back to the, I think, fifth lab session of the solar energy engineering and technology course. Myself, Soumya Tiwari. I'm PhD scholar at Department of Sustainable Energy Engineering at IIT Kanpur. And in the week 5, the lecture has been all about the standalone system. So as usual, we'll go through a brief introduction uh, with whatever the lecture content was, and at the end we'll solve some numerical problems. So standalone system is basically, it's an off-grid system. So to understand it, it's a system in itself that where a power is generated and has it has been utilized. So as the name suggests, it's a stand-alone system, right? So it's basically useful in very remote areas where the power source are not available, or maybe impractical for your basic lighting and other uses, right? So in a standalone system, we have different component. So this is the PV module, where you're mounted on a mounting structure onto your, maybe your roof, or somewhere down the street lamp that you have seen. That is also an example of standalone system. So we have this PV arrays that converts the sunlight into DC current, and your other important component is this charge controller. So basically this charge, as the name suggests, it controls the amount of charge that goes in and out of the battery, so that the battery life can be maintained for a long run. Okay. Then you have your battery bank, in which your energy, whatever energy is generated, that can be stored for further use. And then this whenever your load requirement is there, you can get the basically your current from this battery, depending on whether you are going for a DC load or AC load. If you are DC load, then you can directly utilize this energy, or if you're going for AC load, then inverter is required, where it converts DC to AC current. and whatever surplus energy is there, that can even be sent back to the grid. Okay, so after utilizing whatever your electricity is generated, if we still have some surplus energy, that can be during like peak hour in the sun, that can energy can be sent back to the grid. And similarly, if in a peak load hours where your load requirement is very high, or such, or maybe in the night time when your PV system is not working, if we have power deficiency, then what we can do is we can get the power back from the grid. Okay, so this is the whole component of a normal PV system. So in a standalone system, this is off grid. Okay, so whatever energy is generated from PV module, say, so the typical example is the water pumping irrigation system or street light that you might have seen on the roads, right? So there a PV module is just there, and we have this AC/DC motor, uh, uh, which basically drives the your motor to pump the basically water to your, so basically like a borewell water. So uh, so it can be with energy storage or without energy storage. So the power generated can be directly utilized to drive your purpose, or what you can do is you can store it in batteries, and when your load requirement are there, whether it could be a DC or AC load, with the help of this inverter and charge controller system, you can get your power requirement using these batteries. Now, one hybrid system can also exist where you are using PV module also, and simultaneously you are also using your generators. So it's like a backup generator. So when you have your power, uh, when the generated power from PV system is not, if it, enough to drive your load requirement, then you can use this generator to back up for your various load requirement. So I hope this different type of this standalone or PV system is clear to you. So one by one, each of this component has been um, explored in detail. So I'll quickly go through it all. So battery, you know that it's an electrochemical device that convert chemical energy into electrical energy. So it could be a primary battery or secondary battery. Primary battery are not rechargeable. It once used, it gets exhausted like zinc carbon or alkaline batteries. And secondary batteries are rechargeable batteries, like, so they can convert chemical energy to electrical energy reversibly, like your lead acid batteries used in your household, or a lithium ion battery. So there are two important terms when we talk about the batteries. One is the gravimetric energy density, and another is the volumetric energy density. So it tells us basically about what will be the weight and compactness of the battery. So what we require is we require a very lightweight and compact batteries, right? So gravimetric energy density tells about how much energy is stored per unit mass of the battery. So higher is this value, so in a smaller mass you have you can get large amount of energy, so it will be lighter batteries. And volumetric energy density tells about amount of energy stored per unit volume of the battery. Okay, so higher this value, then more less volume will be required, so more compact batteries will be there. So a Ragon chart is a very famous chart for the batteries, where these two main parameters are on the x and y axis, and you can see how different type of batteries performs as in term of volumetric energy density and gravimetric energy density. Now, coming to lead acid batteries, its oldest mature technology that has been used very in every like household, and very mature technology. So you know the charging and discharging cycle. While discharging, electron flow from this negative to positive terminal or electrode to external circuit, causing a chemical reaction between these plates and electrolytes. So uh, this is a forward reaction. Okay, so this depletes the electrolyte, affecting its state of charge. And when battery is discharged, flow of electron is reversed, and we are not have any external load, but a source with a voltage higher than that of battery enables this reverse reaction. So this is the chemical reaction that we are talking about. And so moving on to next. So high energy density material, or high in, if you are taking for electrode, what it will favor is, we will get the lightweight storage application, like we can use it in lightweight storage application like your mobile. So higher energy density electrode material helps in having your lightweight batteries for your lightweight storage application. Okay, so voltage and capacity. Another battery parameter. Voltage is the nominal voltage at which your battery is supposed to operate. Like 12 volt, 24 volt, and 48 volt are the usually rated batteries. Okay, capacity is basically amount of the charge that battery can deliver at your particular rated voltage. So capacity basically depend on the electrode material you are using. Okay, but so better is the electrode material charge retention or capacity is there, better will be the capacity of the battery. But voltage depend on your the chemical reaction going in the electrolyte. So so voltage depend on the chemistry, but capacity depend on the quantity of active material that we are using. So pay attention to the unit that we are going to use. So capacity measure in ampere hour, charge in coulomb, and uh, uh, your rate of flow of electric charge ampere hour is another unit of charge, and 1 ampere hour is 3600 coulomb. If you're talking about the energy capacity of the battery, how much energy capacity a battery has, it will be your capacity into your voltage, it will be in watt hour. So C rate. C rate is a very important parameter. C rate basically tells that what is the rate of discharge of a battery relative to a capacity. So say your battery capacity is 10 ampere hour. If you're talking about 1C, 1C means 1C rate of discharge means to if you are drawing current from this battery at 10 ampere, it will be fully discharged in 1 hour. Okay, if you're talking about C rate of 2, then the same battery of 10 ampere hour capacity will be, if you're drawing it current of 20 ampere, it will be discharging half of its time. Okay, so similarly, C rate of 0.5 implies that if you're drawing current discharge current of 5 ampere, then it will take 2 hours for that battery to fully discharge. So in general, this statement is important that C rate of n correspond to the battery getting fully discharged in 1 by n hours, irrespective of the battery capacity. Hope this C rate is clear to you. Okay, so uh, now battery efficiency can is a product of its voltaic efficiency and coulombic efficiency. Voltaic efficiency generally it signifies its chemical effect, and coulombic its electrical effect. So voltaic efficiency is your uh, discharge voltage upon charge voltage, and coulombic or Faraday efficiency is your discharge uh, your current upon your, this is basically rate. So q discharge upon q charge, and battery efficiency is a product of these two efficiency, voltaic and coulombic. Now state of charge and depth of discharge. State of charge basically tells about what is the state of charge of a battery. Means um say your 10 ampere hour rated battery has been drained by 2 ampere hour, so its state of charge will be 80%. That means that 80% of the capacity of the battery is still there that can be utilized, so its state of charge will be 80%. And depth of discharge, as the name suggests, the percentage of the battery capacity that has been discharged. So 20% will be its depth of discharge. So these both are complementary. So and the cycle lifetime is another parameter that is used to basically check different type of whether which battery is suitable or not. So it's basically number of charging and discharging cycle before the battery capacity drops to 80% of its nominal value. So higher the cycle lifetime, better is the battery. Low temperature or colder temperature are favorable for higher longer time, and smaller the depth of discharge, higher will be the cycle lifetime. That's true, right? And the temperature effect. So if we are trying to have a good life of the battery, then you need to operate it as lower temperature. But lower temperature also basically the chemicals used in the battery are more active at the higher temperature. So at higher temperature, the battery performance in term of chemical activity is higher at the higher temperature. Okay, so lower temperature decreases the battery capacity, but it's for battery lifetime, the low temperature is more favorable. Now as you use the battery aging also occurs, right? So it's basically due to sulfation. So what happens is, while you discharge if the battery is not fully discharged, what happens is this if you see this chemical reaction, um, some sulfates are formed, right? So if the battery is not fully discharged, what happens is the sulfates crystal start to grow, and that cannot be fully transformed in the your to your lead and lead oxide in your reversible reaction, right? Charging and discharging. So the battery material loss happens. Okay, and that so the battery material loss directly conveys to your decrease in its capacity of the battery. Another reason is the corrosion of the lead grid that you use at the electrode, and also electrolyte can dry out. Also, you might have seen in your household that after few times DI water is used into the battery, your lead acid batteries. From time to time, you have to refill the battery. That is because of at high charging voltage, gassing can also occur, so which could result in loss of water. For that, your demineralized water is used to refill the battery from time to time. Now battery is done. Coming to the charge controller, so as the name suggests, charge controller, what it do is it controls the charge that comes in and out of the batteries. So it's very important a device in the whole PV system, because it basically help in maintaining the lifetime of your battery. So direct coupling of battery to PV array and the load is determinant to the battery lifetime. Therefore, a device is needed that control the current flowing between the battery, PV array, and the load to ensure that the electrical parameter present at the battery are kept within the specification given by the battery manufacturer. Now, so here several function of charge controller are explained. To sum it up, you know that like when the sun is at the peak hour, so the more current might have been generated uh, than the your load requirement. So the overcharging of the batteries may occur, right? That can lead to several other problems like gas formation, capacity loss, or overheating. Or during winter days when low irradiance are there, if the battery has been fully utilized, so over discharging can occur. That is also that affect the cycle lifetime. So uh, to save the battery from this overcharging and over discharging thing, your charge controllers comes into the pictures. Also, we have also studied that PV array are operated such that it always operate at its maximum power point, right? But this maximum power point also depend on the irradiance and the temperature condition. So this battery needs to operate between a particular voltage range, right? According to MPP tracker integrated. So this charge control again helps in running this battery within the given parameters. Okay. Also it can if you want to say the discharge the battery at your required C rate, so you that for that you have to regulate the basically charge or your current. That also, there comes the charge controller in the picture. So these are the different function of the charge controller. Now coming to the cables used in the battery, you know that cables have the resistive loss. We want this loss to be the minimum, and uh, loss can be in terms in I into voltage drop across the cable, or I square into resistance of the cable. So if you uh, as the current doubles, four times as much heat will be dissipated by the cable. So most of the modern modules have connected all cells in series, right? Now this formula, R equal to rho L by A, or 1 by sigma L by A. L is your length of the cable, A is the area of cross section, rho is the resistivity, and sigma is your conductivity. And the typical values of rho and sigma for copper and aluminum wire is given here, and the range are also given here. So so this thing, uh, so this all how it applies to a practical system is very well explained by this example that has been explained in lecture also. So say a 12-volt PV system has two DC appliances, A and B, requiring 15 and 20 watt respectively. The average operational time per day is 6 hours for device A and 3 hours for device B. What is the daily energy requirement? So corresponding to these two DC appliances A and B, one is running at 15 and another is running at 20 watt. This is has to be operated at 6 and this is operated for 3 hours. So you can calculate the energy required by both these devices for per day, right? So it will be 15 into 6 for 6 hours, 20 into 3. This will be 60 watt hour and 90 watt hour. So total will be sum of this 150 watt hour. uh, Note so the daily energy requirement will be, so you have 12-volt PV system, right? So just a minute. Okay, so what is the current requirement from the PV system will be, you will divide this much is your energy requirement, this is your rated voltage of the PV system, you divide it, you can get the current, 12.5 ampere hour current rate actually. Now in addition to the DC appliances, say we have some AC computer and TV set also, whose rated power and running hour is also given. With in now to use this AC current, you need an inverter, right? So inverter efficiency is also given. Now what will be your daily energy requirement? So as done previously, you will calculate it for individual appliances, and the actual DC requirement will be, uh, the actual DC requirement will also, we have to incorporate the efficiency inefficiency involved with the inverter. So the this if this is the your rated energy requirement, but actual DC power that required will be more than this, right, due to inefficiency involved with the inverter. So this will be 306 watt hour, and this corresponding to this, your current your power value will be 306 divided by 12 volt 12 volt PV system. This will be 25.5 ampere hour. Now there are some system losses also, right? You have system losses uh, so considering this system losses, the actual energy requirement will be this AC requirement plus DC requirement. Considering this 20% loss, it will be, you'll multiply this plus multiplied by 1.2. So the energy requirement is 20% more, right? So it will be multiplied by 1.2. This is your actual energy requirement. Now now see, if the sun hour in Guwahati, say this whole load system is in placed in Guwahati, and where the sun hour is 4 hours, so the required total current generated by solar array, that will be equal to your total DC load required, right? So the total DC load required is this, right? So the current generated by solar array will be this is for 4 hours. So for 1 hour you can calculate 11.4 ampere, right? And based on
Excuse me,
this you
ma'am.
can, hello,
Excuse me.
yes.
Yes, ma'am. There is a nominal voltage of PV system is 12 volt.
Right.
and nominal module voltage of cell, that is cell 12 volt,
Nominal
or the
voltage
ratio
of,
of 2 is 1.
can
Then
you please,
which one is denominator and which one is numerator?
sorry, can you repeat it? I couldn't get you what you were saying.
The nominal voltage of the PV system is 12 volt,
Right.
and the nominal voltage of module is 12 volt. The
Right.
required number of module in series 12 by 12. Yes. Then
Right.
which one value is up and which one down?
So
Numerator and denominator 12 volt by 12 volt.
right, right,
Yes.
right. I will tell you. So this volt is 12 volt correspond to your PV system rated voltage, and this 12 volt
Okay.
correspond to your this nominal voltage of your cells, right? So nominal voltage of your module.
Okay, ma'am. Thanks, ma'am.
Got it? So
Yes, yes.
basically, you required only one module that will be enough to basically meet your load requirement, because your rated voltage for PV system is also 12 volt, and your module voltage is also 12 volt, right? So in, if you're talking about what numbers of modules is required in series, then it will be one module, and what number of module required in parallel, that depend on the current, right? So in if you want to know about the number of module in series, you talk about the voltage. If you want to know number of module in parallel, you talk about the current, right? So if this is your required current, and your rated current for your module is 4.9 ampere, the number of module required will be, you will divide this number by 4.9 ampere, and this will be sort of corresponding to three number of module. So hope this thing is clear, how number of modules in parallel and series are calculated for a particular load requirement, and for your particular rated your module system, right? Now, if say the recommended reserve time capacity for Guwahati is 2 days, now we want to use this system at least for 2 days. Even if we don't get power from the grid for 2 days, this system should be operational. So the actual battery capacity will be this required for 1 day into 2 multiplied by 2 for 2 days, right? And considering the 80% battery capacity, the actual requirement will be basically 91.2 divided by zero point 0.8, which will be equal to 1.14 ampere hour. So for this, you again, if you want to calculate how many number of batteries that will be required, so it will be simple, this divided by your rated your voltage, right? Rated current, sorry. So that will give approximate to your two two number of batteries that will be required. I hope this is clear. Any doubt in this? Any doubt in this problem?
No, ma'am.
Okay. So these are design principle and steps. Okay. So so should I explain it, or okay? Just let me reiterate the important points. So our basic design principle is, the generated amount of electricity from the PV grid should be enough to meet our load requirement. So you have to do the power balance along all the component of the your PV system, right? So uh, determining what um should be the size of PV modules, what should be number of modules, what should be number of batteries, that is all things that are involved while designing the PV system, standalone PV system. So uh, you we have also seen that sometimes overcharging or over discharging condition might also be there, right? Depending on your climatic condition and your load requirement. So for that, reliability of for to see the or to give a parameter regarding the reliability of the supply, a parameter has been defined which is known as loss of load probability. Basically it's ratio between your estimated energy deficiency deficit and your energy demand over the total operation time of the installation. So lower this LLP value will be, this means that lesser number of time your whole system will go in your energy deficit conditions. That means your system is more stable and your system is more reliable in term of your supply of your electricity. So this value are the typical values for domestic appliances and telecommunication LLP value. So zero point 0.1 for domestic, 1 for appliances, and 0.001 for telecommunication. So if you see a typical off grid system, so here is your PV system operating at your maximum power point, right? And this is MPPT, uh, that is basically regulating this PV system to operate at always on its maximum power point. This is your charge controller connected to the battery, which control how much charge will go to the battery. So in over charging time it will disconnect the, it's like it will disconnect the power going to the battery, and in similar it will perform in the over discharging time. And this is the DC current. If you want to have fulfill the AC current load requirement, you need an inverter also. So this is from inverter basically convert from DC to AC your load requirement. So this is your typical uh, off grid system schematic diagram. Now this you can go through. These are all the derivation, the power balance along all these particular equipments, along the charge controller and along the equator. When you do the power balance, you will get this different formulas. The important formulas are this one, these two, the alpha and beta parameter. Beta parameter basically tells about relates the PV system, whether the PV system is active or not. Alpha basically tells about the load requirement, whether load is there or not. Okay, so when you do the charge balance, this is the basically your current value. This is going to the battery bank, this is your going to the charge controller, this is going to inverter, and this is your rated voltage of your battery bank. Okay, so this is the final solution that you go get for the what should be the rated voltage of your battery bank. This derivation has been done in the lecture, you can go back to it, see it. So to conclude it, during charging what happens is, so if we, so this is basically your PV system say. Okay, and PV system, this is your charge controller. Okay, and from here you go to the battery, and here is your inverter. Okay, and goes to your load, right? So if the battery is charged, then this ICC is higher than this I inverter current, right? And this beta correspond to this energy balance, and alpha correspond to this power balance. Okay, along across the inverter, and beta along the charge controller. So then beta minus alpha will be your positive, and IBB will be also your positive. So IBB direction is it's charging the battery, so it will be positive, right? During during discharging, what happens is this, your ICC is basically lower than your I inverter, and this beta minus alpha will be negative, and IBB will also be negative. So its direction will change, right? So in this case, you can see that VBB will be higher than the open circuit your battery bank voltage, and here VBB will be lower than VOCBB. So this you can see recommended number of autonomous days at several latitudes. So depending on different latitude zone, what is the recommended number of autonomous day? This means that even your, if you go in a off grid system, like even if your power supply is not get from the grid, how for how many days your whole standalone PV system should be operational. So that recommended number for different latitudes is given in this table. Okay, so now here energy balance is done, and this you can go back to the lecture. The important thing is that you know how this energy balance happens. So even though whatever condition will be given in the question, you can think upon it, and you can do the energy balance, and you can get all the parameters. So you can go back, you can see this in the lecture. This is the application of this whole content that we have seen here. Okay, so a residential house has power requirement of 600 watt for 5 hours every night. Okay, it is proposed to meet the requirement by using a PV array, a battery storage system, and an inverter. The whole system is over designed so that it can meet two extra night requirement even if there has been no sunshine during those days. We have to calculate the number of PV module and the batteries required. Given that the solar radiation is available for an average of 6.5 hours daily, and the average hourly global radiation flux incident on the array is 710 watt per meter square. So this value is given, right? 710 watt per meter square falling on the battery. So falling on the your PV arrays, your battery rating is given 12 volt, 120 ampere each. Depth of discharge is given. Charging and discharging efficiency is given, which is 95%. Inverter efficiency at full load is also given, right? Efficiency of module is given. So efficiency of each module is also given, and this module area is given. So these are all the given parameter in the question. Now we have been asked to calculate what is the number of PV modules. So say there are P number of module. So what is number of module, and what is number of batteries? Say Q number of batteries are required. So we have to calculate this P and Q value. Now if you simply do the energy balance, then your load requirement that you are the load requirement for your 3 nights, so we have to over design it for 2 extra nights. So in total we have to design it for 3 nights, right? And for each night 5 hour operational time is there at 600 watt power requirement. So the total load will be your 600 into 5 into 3, right? This is your uh, load requirement. But basically your inverter is also in your system, right? So there are some inefficiency involved with the inverter also. So the actual power that has been generated by PV module or is getting from the this batteries is not this much but more than this value. And how this will be calculated is the actual required power will be this divided by your efficiency of inverter, right? 0.85. So if you'll do this, you will get your actual power generated by this PV module and battery system, right? At this point. So this is this value. Now this much value of energy has to be generated by PV system and has to be stored in this battery. Now doing more energy balance. So say P and Q are number of modules and battery required. So the coming to the PV array, okay, so the daily energy output from the PV array will be, so this much amount of flux is falling for this much hours onto this much module area having this much module efficiency, right? So we'll multiply all these terms. So note that the area of each module is given. So for P number of module, your whole area will be P into your area of each module, right? Into your number of hours, sunshine hour, into your solar influx, into your efficiency of each module. So this much of energy, daily energy is output from your PV array. Now the total load we have calculated, right? So we have calculated this 9000 watt hour is your total load. What is the power available at the load? So this much power has been generated by PV array, but it has to go through this batteries where its charging and discharging efficiencies are is also there, and then it has to go to the inverter. So these two we have to keep in consideration. So the actual power available at the load will multiply the charging and discharging efficiency of battery into your efficiency of your inverter. So this much power is available at your load. So at this one point this much power is there. So this should be equal to your power requirement. So the energy generated will be should be equal to your energy required. We will equate these two equations, and then you can calculate the number of modules, the PV modules that is required. So it's note that it's in point, so you can take a next higher values to whatever you are getting your answer into. If you're getting into decimal, that will be majorly getting. So 37 number of module is required for this particular load requirement at this particular location. Now the next thing that now we have calculated the number of module. Now we have to get the number of batteries that need. So this much energy, generated energy, need to be stored in this q number of batteries. So if you talk about each battery, so one battery, so energy supplied by one battery to the load, that we can calculate. We know the rated voltage and currents, and we know the depth of discharge and charging and discharging efficiency. We can multiply it. This is the amount of energy supplied by one battery, right? But the actual amount of energy that we require for our load requirement condition is this much. So the number of batteries will divide this total upon the energy supplied by each battery. So this will give the number of batteries required for this load requirement. So it will be around 10 number of batteries is required. So this is all whatever you have studied how to. So it's all energy balance, right? You know, you have to fulfill a load requirement from your energy generated. So we have to see whatever intermediate appliances are there. Considering all its parameters, you need to do the energy balance, and you can get the this number of module and number of batteries. These parameters you can calculate. Hope this question is clear. Any doubt in this question?
No, ma'am.
Okay, fine. Now this is one of another example of standalone PV system where your basically your generated electricity is directly utilized to pump the water, right? So submersible pump we have, we can couple the electric motor with this DC-AC inverter for the power generated from the PV array, and that can drive the basically water from depth from 20 to 100 meters, okay, and supply water around 5000 to 50,000 liters per day. So we can so this is another practical example of standalone PV system. So this is the numerical that will make it more clear how all the in practical scenario how this application is there. So a PV system is installed for supplying water for minor irrigation purpose at a remote place in developing countries. The water is pumped through a borewell from a depth of 40 meter. The PV array consists of 24 module. Okay, and each module has 36 crystalline silicon solar cell arranged in 9 cross 4 matrix. The cell size is given 125 cross 125 meter, and the cell efficiency is given 12%. Now consider the efficiency of inverter and combined motor and pump efficiency of 85 to 85% and 50% respectively. Now we have to calculate the water discharge rate. Water discharge rate, this we have to calculate at noon when the global radiation incident normally at the panel is 800 watt per meter square. Assume the density of fresh water to 1000 kg per meter cube. So what are the given parameter in the question? So this value has been given. So the flux value has been given. This is 800 watt per meter square, right? So okay. So this is 800 watt per meter square. Now what else is given is this number of modules are given. So like this, there are several modules. 24 modules are given. Each module, uh, this has 9 cross 4, 9 cross 4 this solar cell. Each cell size is given, and each cell efficiency is given. Okay. And this efficiency of the pump and motor system is also given, and inverter is also given, right? And densities. So now we have to do all the energy balance. uh, so focusing on each component. So if we focus on this PV array, right? So here our conversion efficiency is given. Okay. So conversion efficiency is given for each cell is given, right? So for each cell, so conversion efficiency will be your power output from this array upon your power input. So your power input is your incoming solar flux upon the whole cell area. So it will be 800, right? Area will be your 9 cross 4 are the arrangement of the solar cell matrix, and each cell has this much area. So this is for one matrix, one module, right? And such 24 such modules are there. So this will be your total area. Okay, so your input power will be this 800 watt per meter square into your total area of the PV array. And your efficiency is given 12%. So you can get what is the PV output, power output, right? Now this is the power that we get from here, right? Now the actual power that is available for lifting water, then we have to consider the inefficiency involved with the inverter and this pump motor system. So we'll multiply this 85% and 50% into this value to get what is the actual power available for lifting the power. So out of 1296 watt, due to inefficiency of this two system, only 550.80 watt is available for lifting the water in your water reservoir. So this much power is basically used to lift water from 40-meter depth. So you know that it will be your potential energy. So rate will be your, this will be m dot g into h, right? Where g is your gravity, h is your height, and m is your mass flow rate. This will be equal to your p power, right? So mass flow rate can be written into density into your volume flow rate, right? These two into g into s. So I hope this formula how it comes, it's clear, right? So this much power is available to actually lift the water to 40 meter height. So we want to know this discharge rate. Okay. So we know the rho value, it's 1000 kg per meter cube. We know the g value 9.81. You know the height, it is 40-meter, and you know the actual power available for lifting the water. This is 550.80. You can put all this value into the equation and you can get the value in meter cube per second, right? This is unit, but the answer, it has been asked in, I think, liter. So it's not mentioned, I hope. So calculate the water discharge. Okay, so you can report the value in meter cube per second also. If not, if it's specifically asked for liter per hour or liter per second, then you have to convert it. So you know that 1 liter 10 to power minus 3 meter cubes, and 1 hour is equal to 3600 seconds. So you can basically use this conversion parameter to get this value in liter per hour. So this is your discharge rate. So I hope this question is clear. Any doubt in this question? Okay. I hope it's clear. So now we'll move towards our question part. So first we'll see some basic theoretical question and then we'll solve numerical problem. Okay. So the first question is cycle lifetime is number of charging and discharging cycle after the battery capacity drops below dash of the nominal value. So what is the correct option for this question? Okay, so I've got option B. Okay, so Shashank has told 80% and C option and B option. Okay, so let's see. So, so the correct answer is option C only. So, just a minute. So the cycle lifetime is number of charging and discharging cycle after the battery capacity drops below 80%. So this I have just told in the class, this live session also. So if the capacity drops below 80% of its normal value, so that is till then is your cycle lifetime. Okay. So the next question is at lower temperature, battery life decreases or increases and battery capacity. What is the effect of temperature on battery life and battery capacity? So we got answer B, right? Okay. So the correct answer is answer B only. Um, so as stated earlier also, at lower temperature, battery life increases, right? So if you operate at lower temperature, your battery will perform much better for a longer time. If we talk about the battery capacity, so some um, materials and the reaction involved perform much better at the higher temperature, right? So that's why the battery capacity decreases, right? So so option B will be your correct option. Now, uh, this is the next question. In PV array, collectors are connected in series and parallel to maximize the value of. So we have got option A, right? Sunil and Shashank has opted for option A. So yes, the PV array, when the collectors are connected in series, we can maximize the voltage, right? And when we connect it in parallel, we can maximize the current. So this I have just explained in the numerical problem. So the correct option will be A option. So in series, say the 12 volt and 12-volt module are there, and in parallel we have, say, this is 3 ampere and this is 3 ampere. So similar to this. So in series, what we can maximize is this voltage value. In parallel, what we can maximize is this current value. I hope this is clear. Now, this is the numerical question, same as we have just solved or seen just right now. I will read out the question so it will be more clear to you. So the question states that a PV system for supplying drinking water is installed in a village in Rajasthan as a part of National Drinking Water Mission. The water is to be pumped from a borewell from a depth of 48 meter. The array consists of 24 modules, each having an area of this much meter square and overall standard test conversion efficiency of 14.1% for global radiation. The conversion efficiency is based on the module area. It is given that the inverter efficiency is 94%, pump and motor set efficiency is 45%. Calculate the water discharge rate. At noon, when the total radiation incident normally on the module is 945 watt per meter square. So this is the question. We have just seen how this question can be solved. I would like each of you to solve, give a try to this question and write your answer in the chat box, right? Has anybody got any answers? Are you guys trying? If you haven't solved it fully, still can you get tell me just the value of power available for lifting water, or power output from array, that value? Okay, do you guys need more time, or should I explain the solution?
Please explain, ma'am.
Okay, okay, fine. So, this was the question, right? So, okay. So this is your PV system. Okay, PV module. Here will be your inverter, right? And with inverter, here is your bore well with your submersible power motor system, right? PM system, and this is your delivery pipe to your storage tank, right? So this system we are dealing with in this question. Okay, this is storage. Now, what's given in the question is the depth is given, right? So the height is given 48 meter, the depth from which water has to be pumped. This is 48 meter. The array consists of 24 modules. So this PV system has several modules. So the 24 modules are there, and each module area is given. Okay, so the area given is, each module area of module is given. This is given 0.5625 meter square. Now the converter, this standard test, okay, overall standard test conversion efficiency is given. So this efficiency is given 14.1. This is at standard testing condition, okay. That standard STC condition is 1000 watt per meter square, right, at 25 degrees Celsius. Now inverter efficiency is given. This is inverter efficiency is 94%, okay. and your this efficient also. Okay, so this efficiency is also given. This is 45%. Okay, and this radiation is given 945 watt per meter square. So this efficiency is at STC condition. Okay, so in normal operating condition, uh, your efficiency will be not as your standard test and condition. So considering the actual conversion efficiency, the say it's at it's to be 80% of this value. Okay, so hope you understand why I'm taking a value lesser than that, because this value is at STC, okay, standard test condition. But in normal operating condition, we are not always operating as 1000 watt per meter square and 25 degrees Celsius. So due to higher temperature and influx variation, there are some more losses that we need to consider. There's thereby we have I have also considered that the actual conversion efficiency is the 80% of this conversion efficiency at STC condition. Okay, so if you consider that, then your power output from the array will be your incident flux. This is 945 watt per meter square into your module area. Your module area is one module area is 0.5625. The number of modules are 24, and the actual conversion efficiency is 80% of the conversion efficiency is at STC. So that you can multiply, and this is the actual power output from the array. Now this is the amount of power that we get at this point. Okay, 1 point. Okay, now the actual power at this point that is actually required, available for lifting water will be, we have to consider the inefficiency of inverter or efficiency of inverter and power motor system, which is 94% and 45% respectively. That will multiply. So out of this much in power generated from the array, only 608.7 watt is actual power available for lifting water. So we can, now this is the actual water that is used to lift, that is available to lift the water mg through this much height. Your height is 48 meter, right? So we will equate this power balance that you will do, and when you equate, we can get this m dot as rho into q, right? Rho into q. So density of water is also given, or you can take 1000. Here it's taken 996. That's also fine. And g value 9.81, and h value it's 48. You can put all this value into the equation. You can get the value in meter cube per second. Now if you have to report it in liter per hour, what you will do is 1 liter is 10 to power minus 3 meter cube, right? So you multiply it with 10 to power minus 3, 10 to power 3. Okay, and you're talking in hours. So so we will multiply it by 3600, convert per second to per hour, right? Then you will get this value into 4672 liter per hour. This uh, problem is clear. So the any question based on this uh, your pumping system will be similar to this only. So the main agenda behind this telling this question is, I hope it's clear how to approach this question. Any doubt in this question? So these are very simple calculations. So okay, so this is the another question. So I'll give some time for you to solve this numerical. I'll read out this question first. So it's similar to what we have discussed. To supply drinking water in village, government has released an order for installation of solar PV system. The water has to be pumped from depth of 51 meter from a borewell. Solar cells are made of single crystal silicon and the array consists of 24 module. Module size is given, cell size is also given, number of cells is given, nominal output, nominal voltage, maximum voltage, open circuit voltage, short circuit current is given, inverter efficiency is given, pump to motor efficiencies, set efficiency is also given. Consider the global radiation incident normally on the cell to be 920 watt per meter square, and the conversion efficiency based on the cell is given 12.5%. Take the density of water to 996 kg per meter cube. Now you have to tell the power output from the array, power available for lifting water, and the water discharge rate. So similar to what we have solved, but I will request you all to solve this question and give me some answer uh, in some values, right? Has anybody got any answers for any of the questions? Like we have three question asked here. For any of the question, any answer? Okay, I'll explain this question. So this was the question. Your again a system previous to what we have discussed is here. A previous system is there with 24 module. Um, with each module size is given, right? And it has cell size is given. Okay, so each module has 36 cell. Number of cells is given. Okay, and each cell area is also given, which is 12.5 cross 12.5 centimeter. Now nominal output and nominal voltage is given, maximum voltage is given, open circuit voltage is also given, short circuit current is given, inverter is there. So we have this inverter. Okay, its efficiency is given. Then we have this pump and motor system is given, its efficiency is also given. And this is your reservoir, right? This is your water reservoir, right? This radiation is given 920. This is 920 watt per meter square. And what's given is cell based efficiency is given. So cell based efficiency is given, which is 12.5%. Okay, this is 12.5%. Okay, now we have been asked the power output from the array, the power at this point. Okay, the power available for lifting water at this point. Okay, and the water discharge rate. So the water discharge rate, say Q here. So we have seen how these problems are solved. So this efficiency, right? So this efficiency of 12.5%. So it will be point 125, right? This will be equal to power output upon power input, right? So this power output will be from PV array, power output from PV array. This will be output upon your power input. Power input is your incoming solar radiation. This is 920 into, this is in watt per meter square. Okay, so into your area, of module will be your, so each cell area is given 12.5 cross 12.5. So this will be 12 point say 5 square. Okay, this is 12.5 into, this is in centimeter, right? So we have to first convert the unit to meter square into minus 10 to the power 4. Okay, this is 12.5 square into, this will be area of your each cell into your, okay, this is area of each cell into you have I think 36 cell as such in each module, and we have 24 such module. Okay, so we will multiply by 24. So this will be your total area. So 12.5 square into 36 into 24 into 10 to power minus 4 for the unit conversion, right? So here, from here you can calculate the power output from PV array. So this will be your correct option will be your I think this will be B option. Okay, let's see. Right, it will be your B option. Now the power available for lifting water. So power available for lifting water at say point 2 will be, this will be your power output from the PV array, which is 1552 155 2.5 into your efficiency of inverter, right? We have inverter here whose efficiency was given 86%, so it will be 0.86, and your efficiency of your power motor system, which is I think this is 48%, right? Into 0.48. So this when you will multiply, so the actual power available for uh, lifting the water at this point 2 will be your um, I think around 640, right? 640.8 watt. Now the discharge rate you can calculate. Discharge rate will be your power available for lifting the water upon your rho into your density. Density is given 996 kg per centimeter cube. G is your 9.81, and your height is 51 meter, right? So you will put all this value and you can get the discharge rate. This you will get in meter cube per second, and you can convert it in liter per second, liter per hour. It's asked in liter per hour by multiplying it by 1000 and 3600. So your answer will be 4629.4. Okay, this will be your answer. So I hope any question based on this particular type of system you can solve in the assignment and in your uh, final exam also. I hope that's part is clear. Now this is another question. So we have a solar PV LED lamp, okay, having a driver efficiency of 85%, operates with a voltage of 3.2 volt DC and draws a current of 0.15 ampere. The lamp is required to operate for 5 hours every night. Consider the configuration of a standalone PV system as shown in the figure below. The PV module efficiency is 15%, while the battery charging and discharging efficiency is 95 and 93% respectively. The battery voltage is 2.4 volt and depth of discharge is 80%. You have to calculate if the daily average global radiation is 4 kilowatt per meter square. So this value is given 4 kilowatt per meter square. The rating of PV module in watt peak. Then you have to calculate the loss factor. If the loss factor of module is 0.9, this is 0.9. What will be the area of module in centimeter square, and what will be the capacity of battery in ampere hour? So this is like cumulative of all the things that you have studied uh, in this module. So I would like all of you to try this question, and even if you get the 10th answer of the 10th question also, please write in the chat box so we can discuss accordingly. Has anybody got any answer to any part of the questions? Okay, I think I've given time. Let's discuss this question. So this was just question, right? So okay. So a solar PV and a LED lamp. So say a LED lamp is here. Your load um, have a driver efficiency of 85%. Okay. So here your efficiency PV to LED lamp is 85%. Okay. This is 85% and operates with voltage of 3.2 volt DC. Okay, this voltage is given 3.2 volt and current is given which is 0.15. Okay, 0.15 ampere current is given. Okay, what else is given? This has to be operated for 5 hours. Okay, every night. So the solar PV should generate enough power so that it can be stored in these batteries so it can operate at night for 5 hours. Consider the configuration of standalone PV system shown in the figure below. PV module efficiency is 15%. So this efficiency is given. Module efficiency is 0.15. Okay. And while the battery charging and discharge efficiency is given, charge efficiency is 95%, which will be equal to 0.95, and discharging efficiency is given 93%. Okay, this is 0.9393. Now the battery voltage is also given 2.4 volt and depth of discharge is given. So this battery rated voltage is 2.4 volt. Battery is there and its depth of discharge is 80%. So its DOD is 80%. So these are all the given parameter in the question. Now what has been asked is this is 80%. Okay. If the daily average global radiation is 4 kilowatt hour per square meter, so it's given 4 kilo. This is in kilowatt hour. Okay, per meter square. What will be the rating of this PV module in watt peak? Okay, so first we'll do the energy balance. Okay, energy required for the DC load, it will be equal to your that is required from battery for each day. It will be equal to P will be load will be your this V 3.2, right? 3.2 into 0.15 and into that has to be operated for 5 hours. So this will be your load power requirement, right? So um, now there are some point driver efficiency is also mentioned, right? So this will be your actual power requirement, which will come around I think 2.4. So it will be 2.4. This will be in watt hour. We are talking about per day. Okay, so it will be watt hour per day. Now the actual amount of uh, load or the power required will be like point, this has 85% efficiency, right? So it will be, so energy consumed considering this driver efficiency will be your 2.4 by this 0.85, right? So considering this driver efficiency, the actual amount of energy required will be this will come around 2.824. Okay, this will be 2.824 watt hour. This will be per day. Okay, so this is the actual amount of energy required to drive this DC load. Now we have been asked for the rating of this PV module. This at the standard test and test condition, that is 1000. So STC is your 1000 watt per meter square, right? This is 1000 watt per meter square and 25 degrees Celsius. This is your standard testing condition, 25 degree Celsius. This is your STC. So if we try to calculate, understand in term of STC, so the PV module are rated for standard value of solar global radiation, that is your 1000 watt per meter square, and when the solar cell are maintained at temperature of 25 degrees Celsius. So we will use the given daily minimum global radiation of this 4 kilowatt hour per meter square in our calculation, and we will understand it in form like interpret it is to equivalent to 1000 watt per meter square for 4 hours, so that will be equal to 4 kilowatt hour per meter square. I think uh, that is clear, right? So if we try to interpret this in term of STC, what we can say, we are receiving 1000 watt per meter square for 4 hours. So it will be 1000 into watt per meter square into 4 hour, which will be equal to 4 kilowatt hour per meter square. So if we calculate the PV module wattage, so required, so it will be your required your, so now, okay, so if you're now we have calculated till now, we have to do the energy balance till here also. So for that we'll include the efficiency involved with the charge controller and your battery. Okay, so this will be your this value will be divided further by your this 2.824 divided by your charging and discharging efficiency of the battery, which will be 95% and 93%. So that will come around 3.196. Okay, so that will come around 3.196. This will be in your same unit, watt hour per day. Okay, this will be watt hour per day, right? So we are talking about this point. Okay, now if it try to calculate the PV module wattage, so we'll divide this by 4. Okay, so we can calculate the rating of the PV module, and that will come around, I think that will come around point 0.8. So if we multiply it, then it will come around point 0.8. Now we are this the rated power is at the STC, but in actual condition, cell is not always operating at 25 degrees Celsius. So some are it's generally higher temperature only. So that will also include two extra losses. So for that, the loss factor is included zero point 0.9 for the module. And considering this, the area of module has been asked. So this much energy, like this much 3.196, has to be generated by the PV module. Okay, so this energy balance that you can do is, so your this will be your 4 into 1000. Okay, this is your incoming solar flux, 4 into 1000, and into your area, say the area is A. Okay, and your efficiency of your module is given right in the question. So it's given, um, so okay, so it's given 0.15. Okay, PV module efficiency is 0.15, and the loss factor that we have to include for the module, that is zero point 0.9. So we'll equate this, basically it's energy balance only. Okay, so this is your incoming solar flux, this is your area, this is your efficiency, right, and this is your loss factor. So this is, so you will, when you will do the energy balance, you can calculate the area, and you can get the area in you note that you will get area in meter square. Okay, this area will be in meter square, you, and the answer, it is asked in centimeter square. So change it to the centimeter square, and the value will be 59.2 centimeter square. Now to calculate the capacity of battery in ampere hour. So we know the energy consumed here, right, by the battery. This capacity of the, basically capacity of batteries, so this will be, capacity of the battery will be equal to your energy consumed, which is this much energy. This much energy is actually consumed, and at this point, right, and divided by your battery voltage, your battery discharging efficiency, and your depth of discharge. So the capacity of battery will be, so if you remember the formula EV, right, the energy consumed by battery will be your rated voltage of the battery into your capacity of the battery. Now if we have to also see here only discharge efficiency. Okay, because while discharging only, you are providing power to the LED lamp, and then we have also have to consider the depth of discharge. So it's not like 100% of the battery could be uh, discharged. Okay, so this, when you equate, so this is EB. Okay, now this value has been asked, CB value is asked. So EB, you know that energy consumed, this is your 2.824, right, so this is 2.824. Voltage or rated voltage of the battery is given 2.4, so 2.4 into capacity of the battery, this is capacity of the battery, into your discharging efficiency, your 90, I think 93%, right, so it will be into 0.93, and depth of discharge is 80%, so into 0.8. So you can solve this energy balance thing, and you will get this capacity of battery to be 1.58 ampere hour. So I hope this question is clear. So it's on whatever the thing that you have studied for standalone system, how the, how much battery capacity is required, how much area of the module is required, how to, so how the practical application of this, all the standalone system and the formulas that you have studied, it's well explained by this question. uh, I hope this question is clear. Any doubt in this question? Any doubt in this question, or in any of the question till we have discussed till now? Okay, so we are way beyond our time. So thank you all for listening. Hope this session was useful to you, um, in solving the, will be useful to you in solving the assignment and your final examination. If you have any doubt, feel free to ask in the next session. Till then, I will end this session. We'll meet in the next session. Okay. Thank you all.